We're going to dive right into weak acid and bases with section 8.3. So, in general, anytime you have an acid that dissolves in water, we have this reaction take place where the acid is represented by the HA, and then it reacts with water. So in this case, we're labeling water as the base if we have a different acid reacting with it. Remember, water can be amphoretic, so it could be an acid or a base, whatever the situation is. And when that happens, we form the conjugate acid, which is the thing that is formed when the proton transfers to the base, and that is our hydronium ion. And then what's left over after the acid loses that H plus ion is what's known as the conjugate base, and represented by the A minus. And the conjugate base is everything that's lost, everything that remains after the acid loses one proton. So we have what are called conjugate acid-base pairs that contain two substances that are related to each other by the difference of a proton, okay? So the pairs turn into, for this example, we have the acid goes with the conjugate base, and the water, the base, goes with the conjugate acid. So the pair is the acid for the reactants gets paired with the base of the products, okay? It's never acid-acid, it's always acid with a base. And so then the other pair is the base pairs up with the conjugate acid. And so don't get confused when it says a conjugate acid-base pair. Even though it says acid first, sometimes the base would be first, okay? It just depends on the situation. They just match together that way. So when we have acids reacting with water, there is a competition for that proton. Remember, the proton is the H plus ion. So when there's this competition, this helps us to figure out whether or not there will be a strong acid or a weak acid. So if the water, which is the base in the situation, is a stronger base than the conjugate base, the A minus, which means that the water has a greater attraction or affinity for that proton than the anion does, the conjugate base, then the equilibrium will lie far to the right, which means that most of the acid is going to dissolve. So it will be ionized, it will dissociate, and that would be considered a strong acid. So if the acid likes to be broken apart, if it's not too much to break it apart, then it will be a strong acid. It will completely dissociate. That's what that means. Now, if the opposite is true, if the conjugate base is stronger at attracting that proton, accepting that proton, than the water molecule is, then the equilibrium position will lie far to the left, meaning that most of the acid will not dissolve and will be present in its original form at equilibrium, which shows us that it is a weak acid, because weak acids do not dissociate as well. Okay, so because they don't dissociate when dissolved very much, then we have to use equilibrium expressions to help us to determine the amount that has been dissolved. So the following calculations are not needed for strong acids and bases because they completely dissociate. Okay, so just be careful there. If it's a strong acid or a strong base, then you don't have to do all of this information, all this extra work sort of thing. So going along back with our reaction that we had with the HA plus the water to make the hydronium plus the conjugate base, we have this equilibrium expression set up where Ka is called the acid dissociation constant. It's very similar to the equilibrium K rate constants that we had before, or the equilibrium constants. And I have both sets here for you, depending if you're including water or not, but the hydronium and the H plus are commonly used to represent the hydrated proton, and they are interchangeable, but the AP exam prefers the hydronium. And when you set these up, just remember, in case you're wondering, we don't include solids or liquids because their concentrations will not change. So liquid water was a reactant, but that's not going to be included in our expression because it is a liquid. It's not an aqueous solution. So we say that it's just constant and not included. So when we have to calculate the pH of a weak acid, we have to calculate the pH, but it becomes a little bit more complicated, where we will have to use equilibrium expressions, hopefully not the quadratic formula, but possibly if we cannot make an assumption. And then we'll determine the hydronium concentration, which then can lead us to solve for pH. So we have to do the equilibrium ice chart first to solve for our concentration, to then plug in to our pH equations, which just makes it a little bit more difficult. So when we look at the problems, we're going to look at the major species in the solution, and then write the balanced equation so that we can figure out where the H plus is coming from. Then we use the values of the equilibrium constants for the reactions so that we look at those to decide where will the dominant be in producing the hydronium or the hydrogen ion, the proton. So then we'll be able to write the equilibrium expression. Then we write out our ice chart with determining listing the initial concentrations, defining the change. I watched an AP video and I liked it, so I'm going to try my best to do it myself. I'm not used to it yet, but when it says define X, what this teacher did is when you are dealing with acids, they used A instead of X. And when they used A for acid, and then when it was a base, they plugged in a B instead of X. So I like that. It's a nice little reminder of what you're dealing with, so you are keeping that in the back of your mind. So I'm going to try and do that myself. And then once you know the equilibrium expressions, then we'll be able to then calculate the hydronium concentration, and then that would lead us to pH, like we did in 8.1 and 8.2. Okay, so here we go. A hypochlorite ion is a strong oxidizing agent often found in the household bleaches and disinfectants. And it forms hypochlorous acid, which is HOCl, and there is a Ka value associated with that. So calculate the pH of a 0.1 molar aqueous solution of hypochlorous acid. Okay, well, we have two things involved here. We've got the hypochlorous acid, we've got the water. Those are our two main species. Well, in this situation, the acid has our Ka value, right? And so the acid is going to be what is going to donate, what's going to it's going to be what gives the concentration for the hydronium ion, not the water. The water is going to act like a base here. So we're going to use that equation. And this time I'm going to actually plug in everything. So our acid is the HOCl, and water is going to act like a base this time, where we will then form the hydronium, and then the conjugate base is the leftover after you take off an H and after you take away one charge. Okay, so that's where we get that hypochlorite ion. So now, figuring this out, we've got our ice chart, right? So initially, the concentration of the acid is 0.1 molar. I'm not going to put significant figures right now. The water does not need anything because it's a liquid, so it's not important. And we don't have any ion concentrations to start. So we're assuming that we're going to first start this dissociation. So then for the change, we always add to the side with 0 and subtract to the sign with not. So I'm going to use A here instead of X because we're dealing with an acid. So plus A plus A. So at equilibrium, the concentration of the acid will be 0.1 minus A, and then the hydronium and the hypochlorite ions will both be equal to A. No coefficients here, which is nice. Okay, so at this point then, we can plug in and solve for our hydronium ion concentration, or the A. Okay, so our Ka expression, in case you need to see it, is going to be the hydronium concentration times the hypochlorite concentration all over the acid concentration. And so then substituting in what we've got, we will have the 3.5 times 10 to the negative 8 is equal to A times A over 0.1 minus A. Now, this is a small, like we're going to do a lot of assumptions in acids and bases. So times 10 to the negative 8, we're going to assume that the A value, what we're going to solve for, is so significantly small that it will not really change very much the original concentration of the acid. So we can take it off anywhere it's added or subtracted. Okay, so then now simplifying, we've got our 3.5 times 10 to the negative 8 is equal to A squared over 0.1. And when I solved, I got that A equals 5.9 times 10 to the negative 5. Okay, so if we look back briefly, we said that A is going to be the hydronium concentration at equilibrium. So this value that we just got is actually the concentration, so molarity, molar label, of the hydronium ion. So then now that we know this hydronium ion concentration, we can solve for pH using our equation that the pH is equal to the negative log of the hydronium concentration. Okay, so negative log of the 5.9 times 10 to the negative 5 is 4.23. So it's a little bit more work to get the pH of a weak acid because we have to do all the ice chart first to solve for what the concentration is. Also, don't forget, I forgot to mention, the rounding, whenever you are solving for the pH or the POH, make sure that you notice the number of sig figs that are going into the log function, because that tells you the number of decimals on the answer outside of it. Okay, so now what happens if we have a mixture of weak acids that have different strengths? How do we figure out the pH? Okay, the steps are the same as followed in example 4, but it's important, something else to compare. Okay, this is just a little side note. Ka values help you decide strength or help determine strength. Kas determine strength. So when you have a large Ka, then that means that it's going to be the dominant or the acid to dissociate the most. Or in a situation of a mixture, that would be the dominant acid. And so if it's the dominant acid, then that's the acid that's going to provide the hydronium ion in order to find pH. Okay, so we're going to look at a mixture of acids in example 5 and compare Ka values to decide which one does actually help determine this. Okay, so we want the pH of a solution that contains 1 molar of hydrocyanic acid, HCN, which has that Ka value, and 5 molar of the HNO2, which has that Ka value. Also calculate the concentration of the cyanide ion in this solution at equilibrium. Now, first of all, what are our major species? What is going to be present in this beaker? Well, we have our HCN, we have our HNO2, and we also have water. So we're going to, since we're comparing the Kas here, we're going to compare them all. We're going to throw in water, right? So the major species, the things involved are the HCN, the HNO2, and water. Okay, so let's compare K values, because it's KW for water, of all these things, right? So the HCN has the Ka of, that's wrong, 6.2 times 10 to the negative 10. The nitrous acid has a Ka of 4 times 10 to the negative 4. And water, since we're comparing here, Kw is 1.0 times 10 to the negative 14. Something to remember from before. Okay, so looking at these Ka values, the largest of all the Ka values is the nitrous acid, the times 10 to the negative 4. So that means that since that is the largest one, that is going to be what contributes for all of our H plus or our proton, that then would give us the pH value. Okay, so when we are figuring this out, we're going to forget for now anything about the HCN and anything about water. We're just going to focus solely on the HNO2. Okay, so with our equation, we've got the HNO2 reacts with water to form the hydronium ion, and the conjugate base here would be NO2 negative. Okay, so again, we're going to just forget about that 1 molar part right now. We're just going to include this 5 molar as our initial concentration, and we got zeros. We're dealing with acids, so I'm going to add acid, subtract acid. So at equilibrium, sorry, I'm not filling this all in. We got 5 minus A for the concentration of the acid, and then A is equal to the concentration of the hydronium and the nitrite ion. Okay, so next let's do, we're following along right now with the rest of example 4, where we're going to substitute in and solve for A. So this time, remember, we're using the HNO2. So the Ka value for that is 4.0 times 10 to the negative 4 is equal to, and I'm just going to simplify here, A squared over. Now, I know that it's a big number, but like I said, we're assuming that since it's a weak acid, only very small parts will actually dissociate. So anytime with an acid, we're just going to go ahead and make the assumption, okay, that it's such a small, insignificant amount to the original that it's not going to change anything. So we can take off those plus and minuses. So it'll just be divided by 5. Okay, so then to shorten it a little bit, I was able to solve for A, and I got 4.5 times 10 to the negative 2. So this is our molarity, which is then, if we look back at our ice chart, that is the concentration of the hydronium. So that will allow us to solve for the first thing that the question asks for. It is asking us to solve for the pH. There's another thing that it asks for us to solve for, but first of all, pH. So let's do that next. So for the pH, take the negative log of 4.5 times 10 to the negative 2, and I got 1.35. Okay, so that's the first thing that we were asked to solve for. The other part of the problem is we need to calculate the concentration of the cyanide ion at equilibrium. Okay, so this is where we can have this mixture. Even though we've already looked at the major species, we have figured out at equilibrium what the concentration of the hydronium is. So that is going to play a factor into setting up to solve for the CN, the negative, the cyanide ion. Okay, where now this is the second part. So we're thinking about our HCN here because that contains the CN portion. Okay, so when I set up my expression for Ka, I have my hydronium times my cyanide over, now this is a concentration of HCN. Okay, well, Remember I said that we already know the H3O plus, we already know hydronium ion, we already know Ka as well. So the Ka value for the HCN was 6.2 times 10 to the negative 10. Then this is at equilibrium, so we already know the hydronium. We just solved for that recently, so that's the 4.5 times 10 to the negative 2. We don't know the CN concentration, we're solving for that. But now the denominator. We didn't do an ice chart to solve for what it should really be for the change with the HCN. But I said this before, when you have a weak acid, a majority of it is not going to dissociate. So we can make an assumption, since we've already assumed some other things, we can assume that in the original problem, we were given that the concentration of the HCN is 1 molar. So we will assume that even if we knew what the change was at equilibrium, if we rounded it, it was probably still going to be 1 because it was going to be such a small change. So I'm just going to keep in the bottom for my HCN concentration my 1.00. So we're dividing by 1 here. So then now it's a lot easier to find that concentration of CN because all we have to do is take our Ka divided by our HNO3 or our hydronium ion. So then I got the concentration to be 1.4 times 10 to the negative 8 molar. Okay, so this is just taking in some of those principles of like how do we compare Ka values, how do we look at all that stuff, okay? So we mentioned this before, but our sulfuric acid, one of our strong acids, is we called it diprotic. It's polyprotic, meaning that it can dissociate and have multiple protons, okay? Now, diprotic specifically stands for 2, and triprotic stands for 3 protons. And I don't really think that we have more than 3 acidic protons, but for a typical weak polyprotic acid, you will have multiple Ka values, okay? And so the 1, the 2, the 3 depend on how many you have. So normally we have 1, so this doesn't matter, but if you have something like sulfuric acid, you will have 2, and if you have something like phosphoric acid, you will have 3 Ka values. And this is a representation to show that as you work your way down, the value of the Ka for each proton will get smaller and smaller. So it means that it's going to be harder and harder for you to lose that acidic proton each step of the way, okay? So how does this come about? Well, look at carbonic acid, okay? Now, on these expressions, I'm not including the water situation, hydronium, I'm just using H+, but remember, they're interchangeable. So the carbonic acid, H2CO3, has 2 acidic protons, okay? So when we lose 1 proton for the initial dissociation, we get the Ka value here. It's given in the table. But this is going to be important right here. The conjugate base. Okay. The conjugate base from the first step, when you lose only 1 proton, okay, notice how there's still an H there because there was a 2 to start and it has a -1 charge because it was normally neutral. Then that conjugate base, if you were to do another calculation, becomes the acid in the next step. So it's right here again, okay? And then when it's the acid in the next step, then it can lose its second acidic proton to then make the final conjugate base, the carbonate ion. And that's how you would be able to solve for and get the second Ka value, okay? So this is just how that comes to play when you have these steps to try and show you that, okay? So you have this table 14.4 in your notes where it has the series of the stepwise constants for some polyprotic acids. Notice for the sulfuric acid, remember that's a strong acid, it just says large, which means that it's definitely going to lose it. Okay. If you remember, the larger the Ka value, the more likely it'll lose its H+, its proton. Okay. So there is also a table of Ka values in Appendix 5.2 in your textbook, so that might be helpful to find that when you're working on problems. And it's also another way that we can look at Ka values is that the negative charge, as the negative charge on the acid increases, it becomes more difficult to remove the positively charged proton. So that's why the Ka values drop so drastically. So when you have to do stepwise, it's just a lot of work. It's not that difficult, but it's just like keeping in mind where everything is supposed to be, because at equilibrium, remember, like, so when something's at equilibrium, that number is not going to change anymore. But we're going to have an example partially of a problem here right here in a second. Okay. And so, also, I kind of said this. The only dissociation that's most important for the contribution of the H+ comes from that first lost proton. So that's that first lost proton, like the Ka value, would be what you would use when you solve for that to get pH. Okay. Everything else doesn't really have that effect. So example 6, this may or may not say example 12 in your notes. I apologize if it does. Calculate the pH of a 5 molar phosphoric solution and the equilibrium concentrations of the species of the phosphoric acid and the first conjugate base of that. We're actually going to take it a step further because I cut this problem down and then realized I wanted to do more. So you're just going to be smarter than other people in class. It is fine. Okay, so the first thing we have to do is we're just losing one proton at a time. Okay, one proton at a time. So we have to start with the original acid. Okay. Now back on the table from table 14.4 in your notes, I'm getting these values. So for the phosphoric acid, the Ka1 is 7.5 times 10 to the negative 3, and Ka2 is 6.2 times 10 to the negative 8. And there is a third one, but we're not going to use it. So we don't have to worry about that. Okay. So for the first acidic proton, okay, the phosphoric acid is going to react with water to form the hydronium, and then this H2PO4 negative is going to be our first conjugate base. Because we've lost one H, we've decreased the number of H's by 1, we've decreased the charge by 1. Okay? Initially, we have 5 molar of our acid. Don't worry about the water. 0 hydronium, 0 conjugate base. Okay? So our changes are like what we've seen so far. And at equilibrium, 5 minus A, and A. Okay. Well, now let's solve for A, the hydronium, because we need the pH. That's one of our things we need to solve for here. Okay, I just cross it out. The Ka, we're going to use the first Ka value because it's the first proton lost, is 7.5 times 10 to the negative 3 is equal to, simplifying here, A squared over, remember, we're just assuming that since it's weak acids, everything can make an assumption, over 5. So then the A for this problem is, now this is not, I guess I can round it correctly, is 1.9 molar. There, that would be correct sig figs. I don't have a correct sig figs in my notes for some reason. Okay, so then this is the hydronium ion concentration. So then that leads us to find the pH. When we take the negative log of that, and maybe this is why I had it so that when I took the negative log, I had the best answer. I got 0.71 for the pH value there. Okay, so that's not the end though, because we need to know the equilibrium concentrations of all the two species that we have, okay? So at equilibrium, this technically is an answer. At equilibrium, the H3O plus is equal to that. So that's one of the answers. That's also equal to the A for the H2PO4 negative. So that already gives us this answer, okay? So that's that, this is that. And then if I were to subtract, I technically had 5.0 minus the 0.19, so I need to keep one decimal place here. So that would be 4.8 molar. So this is the other part of the problem that it wanted you to have, okay? So don't get too confused if it's not too bad. What we could do, and I'm going to save some time and not do this, is you could, then what would happen if you had to keep going to keep losing protons and finding out more information, then you would plug in the 0.9, the 0.19, the 0.19 in different spots and go from there. If you would like more clarification on this or to see what would happen with that, you can look at example 14.15, 14.15 on page 682 in the textbook for more work with that. Okay, it's important to note that sulfuric acid is our only strong acid that is also polyprotic. So the first proton's easily lost, which makes your initial calculations just like you would for the strong acid, but then you need a Ka value for the second proton because it's not going to be easily lost. Only in dilute polyprotic acid solutions does the second dissociation step contribute significantly. So if you want more information on this one, look at example 14.17 in the textbook, which is on page 684. And then another summary of characteristics of more polyprotic weak acids is on page 686 in your textbook. So you can read up a lot more on this if you would like to. Now let's talk about weak bases. Remember, the definition of base that we're going with here is that they accept protons, right? So many type of proton acceptors don't actually contain hydroxides, but they can increase the concentration of the hydroxide ion when they react when dissolved with water. So this is an example here of a non-hydroxide containing base, where the NH3 is called ammonia. We've seen it quite often. NH3 is ammonia. Okay, so this is going to be our base. And it reacts with water. So this time water is going to be an acid because it's going to give this hydrogen over to our base. And since it's donating its hydrogen, it's going to be an acid in this situation. So then right here, there should be a plus sign there. That would be it's called ammonium. That would be our conjugate acid that is formed because it's what has happened after you gain the H plus. And then the OH negative, our hydroxide, is our conjugate base sort of situation. So even though it doesn't contain hydroxide in its actual formula, it still contributes by the way that it interacts with water to increase the hydroxide concentration. So there's a whole bunch of different types. We got methylamine, dimethylamine, trimethylamine, ethylamine, pyridine. All these things have a general reaction with water to increase the hydroxide concentration. So since A, we used acid, or we used acid had an A for base, we use B for the generic. So this is our generic equation where B stands for a base. When it reacts with water, which is acting like an acid, then we create the conjugate acid and the base there. Okay, and so then we get Kb expression, which Kb is the base dissociation constant, and the B just stands for base. So it's always referring to the reaction of a base with water. So in these situations, I know in my notes I've had both. I've had sometimes where the acid reacted with water and sometimes where it didn't. But with base, you definitely have to have water as a reactant in order for you to correctly write it to produce that hydroxide, which is the important part of the whole thing. So there are a lot of different types of weak bases, but you just want to make sure that they have a KB value. We're going to use the ice chart to solve them. But also you have to realize that when you solve for the value from your ice chart, it's actually going to be the hydroxide concentration, not the hydronium or the H+. So to get pH from that, it's going to be a little bit more difficult. You have to have one more step added in. But there's a table here, table 14.3. There's another table. I think it's right around the other appendix that I mentioned before about weak acids in the back of your textbook. Okay. So let's just see how it has that extra step, okay? So we want to calculate the pH for a 15 molar solution of ammonia. That is very strong with a KB value that's the given. Okay, so remember when we write out our expression, we always have to include water because that's the way that you create hydroxide. So the ammonia plus water makes the NH4 plus 1 and hydroxide. Okay, and initially we have 15 molar for the NH3, nothing for the other two. So I'm going to use B's. This is where I mentioned this a while ago, but that other teacher used A's and B's and I liked it. So she thinks use a B because then that helps remind you that you have to do that extra part to get the pH at the end for a base. So I'm going to try it. At equilibrium, the concentration of ammonia will be 15 minus B and B for both of those. Okay, so then remember, we're going to still set it up products of a reactant, but this time we're going to use our KB value. And it's going to simplify down into B squared over 15. Because we're making assumptions, because we've set it up the correct way. If you're having trouble with this, I know I'm trying to skip ahead to save some time. Please ask me and I can help you about it. Okay, and so when you solve for B, that gets you 0.016. Okay, so that number is the hydroxide's equilibrium concentration. So that B value is our hydroxide. If you look back at all the equations from 8.1, if we take a negative log of this number, we're not going to get pH, but we're going to get POH. So to get our answer at the end, we're going to have to do two steps. So what I do is I would take the negative log. It's simpler, I like it, of our value we just got. And I got that to be 1.78. So this is POH, not pH. Okay, so then to find pH, we just have to subtract from 14. Now be careful, we want to keep 2 decimals at the end to keep all of our sig figs accurate. So that's why I like to write down the 14.00 so I remember that. And you get 12.22 for the final pH. So it's for weak bases, it's basically the same, but you just have to make sure that you realize that you solve for the OH concentration, not the hydronium concentration. So we have to do one final step to get to the pH at the end. Other useful equations here. This top one, the Kw is equal to the Ka times the Kb. That will be useful if you ever are only given a Ka, but you find that it's actually going to be a basic solution, so you'd rather use the Kb. So that's a nice relationship to remember. And then just like we have pH and POH, anytime you take a negative log of something, that we signify that by putting a P in front of the number. Later on this unit, we're going to talk about pKa versus pH. So having that equation is helpful. Okay, last but not least in 8.3. we have just percent dissociation, or sometimes referred to as percent ionization. So the exact amount of weak acid that has dissociated or ionized in achieving equilibrium can be determined by our percent dissociation method, where the percent dissociation is equal to the amount dissociated divided by the initial concentration times 100. Another way to think about this, when we're solving, the top value will be the concentration of the hydronium ion, because that technically, when we do an ice chart, is how much is dissociated, right? Over the concentration of the acid, which is the original amount. How much did it start out with? Okay. And so for a given acid, weak acid, the percent dissociation will increase as the acid becomes more dilute. That's just something to remember. Okay, so our last example. We want to calculate the percent dissociation of acetic acid with that Ka in a solution of 0.1 molar of the acid. Now, I have been using the full acid terms to make the conjugate bases, but here, acetic acid is a very big formula, so I'm just going to use simply HA for this. So I'm talking about this, but I'm going to denote it in my problem as HA. And the A just stands for the ion or the conjugate base, you know, in that situation. Save some time, okay? So with our acid dissociation, we have to solve for the hydronium concentration to be able to plug that in for our equation, okay? So initially, we've got 0.1 molar of the acid, 0 for both of those. We're adding A, subtracting A. We're acids again here, so that's why I'm using the A's. So 0.1 minus A, and A, and A. So let's solve for that A, shall we? The part that's dissociated, the part that's broken away, that's now turned into something new. So our Ka value is equal to the hydronium times the conjugate base over, we're assuming that it's going to be so small that it doesn't really impact it, so take it off. Okay, A is, when you solve for it, 1.3 times 10 to the negative 3 molar. All right, so this amount is the amount that has been dissociated. So this number right here is going to go in the top or the numerator of our ratio to find the percent dissociation. Okay, so for the percent, we're going to put this 1.3 times 10 to the negative 3 in the numerator. The denominator is the original acid concentration, which was the 0.1. So you divide those up, divide by 100, and the dissociation percent was 1.3%. So that means that 1.3%, what that means is only 1.3% of the original acid has broken apart. So 99.7% of the acid is still intact. It's still together, not dissociated. Its ions haven't broken apart. So that's why we have all of these complicated calculations for it.